Hi everybody, Namaste and welcome to Murali's World of Physics once again. The universe in which we live is a very vast and limitless entity. So is the world of numbers. These numbers are of importance not only in mathematics but in almost every other branch of knowledge. Such limitless entities are termed as infinity. In fact, in the world of numbers, there is a multitude of levels of infiniteness. Let me explain what this means. As a child, we start learning the numbers using the integers 1, 2, 3, etc. up to 10. For the child, that is the end of the world of numbers. But later on, he realizes that no, that is not the end of the world of numbers, but there are numbers beyond that also. Maybe up to 100? Well, he will realize that, again, that is not the answer. There are numbers beyond 100 also. Very soon he realizes the infiniteness of the world of such numbers. I mean the integers. Now, later on, he starts learning about decimal numbers. So he is introduced to numbers like 1.1, 1.2, 16.1, etc. So those are the numbers with a single decimal digit. So that forms the next level of infiniteness in the world of numbers. Now let us take, for example, two adjacent numbers with a single decimal digit, say 8.1 and 8.2. Now the child then learns that there are numbers between these two adjacent numbers. These are the numbers with two decimal digits, like 8.11, 8.12, 8.13, etc. up to 8.19. So that is the third level of infiniteness, and so on. So if one takes two adjacent numbers with n decimal digits, you can see immediately that there are numbers in between these two with n plus 1 decimal digits. So like that, the multitude of the levels of infinity in the world of numbers unfolds in front of the child. He can go on counting the numbers in this fashion for hours, for days, for years, and still he cannot get to a stop. There is no limit. Thus, there is no end to this procedure. That is the infinite multitude of levels of infinity that I have referred to above. So in this immense expanse of the world of numbers, there are certain unique numbers which are of importance in mathematics and physics. So in this video, we will be exploring some of those unique numbers in this vast expanse of the world of numbers. We shall start with some unique numbers in mathematics. Some of these numbers are integers, whereas most of them are irrational numbers which cannot be represented as the ratios of integers. We'll first start with integer numbers which are unique in mathematics. The first set of numbers which are of importance in mathematics and elsewhere, and the one which comes to my mind first is the set of prime numbers. Now these are integers which are such that they do not have any factor other than the number 1 and the number itself. That is, they have only two factors, 1 and the number itself. Other numbers which have at least three factors, including 1 and the number itself, are called composite numbers. 1 is not considered as a prime number. So naturally, the first prime number is 2. Next comes 3, then 5, 7, 11, 13, etc. In fact, these numbers form an infinite set. Except the lowest prime 2, all the higher prime numbers are odd. Also, excepting this lowest prime number 2, the sum of any two adjacent or any two prime numbers will be an even number and therefore a composite number. The case of number 2 is slightly different because the sum of 2 with any other prime number can be either a prime number itself or a composite number. For example, 2 plus 3 is equal to 5 is a prime number. Then 2 plus 5 is equal to 7 is also another prime number, but 2 plus 7 is equal to 9 is not a prime number. Again, 2 plus 11 is equal to 13 is another prime number, and so on. The number 2 is also unique in being the base of the binary number system, which is the soul of the entire world of digital electronics. Any composite number can be written as the product of 2 or more prime factors. This is a fundamental theorem of arithmetic. Thus, prime numbers are considered as the building blocks of numbers. The first number is of course 2. It is the only even prime number, because any other even number will have at least one more factor. So therefore, the list of prime numbers will run as follows. Of course, 2 is the first prime number, then 3, 5, 7, 11, 13, 17, 19, and so on. So you can see that all these are odd integers. The largest non-prime number as of November 2020 is 2 raised to 82,589,933 minus 1. So that minus 1 makes it a odd number. So this is a number that has 24,862,048 digits when written in the base of 10. Every even integer bigger than 2 can be split into 2 prime factors. For example, 6 is equal to 3 plus 3. Again, 8 is equal to 3 plus 5, and so on. To list all the prime numbers greater than 40, one can use the formula P is equal to n square plus n plus 41. N is equal to 0, 1, 2, 3, etc. This is illustrated here. N is equal to 0 will give us 41, which is a prime number. N is equal to 1 will give us 43, which is also a prime number. N is equal to 2 will give 47, which is the next prime number, etc. The integer 10 is also a unique number. It is the base of the decimal number system, which is so common in our day-to-day dealings. It is interesting to note that 10 is the sum of the first 3 prime numbers, namely 10 equals 2 plus 3 plus 5. A practical way to list all prime numbers less than a given number, say 50, is what is known as the sieve of Eratosthenes. Here what we do is we write out all the numbers up to 50. Then circle the number 2 first, since it is the first prime number, and then erase all its higher multiples, because these are all even numbers and they cannot be pi. That means the composite numbers which are even. Move on to the next non-erased number, the number 3. Erase all its higher multiples of 3 also. Now we repeat the same step for the next non-erased number and so on. Now this is the sieve of Eratosthenes. So we, of course, 2 and 3 are prime numbers. Then we erase all even numbers. Then all multiples of 3, namely 9, 6, 12, 14, 18, etc. Then all multiples of 5, so 10, which is already erased, 15, 20, etc. So in this fashion, we erase all multiples of the numbers which appear first in that order. And then what remain will be the sequence of the prime numbers. 2, 3, 5, 7, 11, 13, 17, 19, etc. So that way one can generate all the prime numbers below a particular maximum number. There are what are called circular primes, which is defined as the one which has the property that the number generated at each intermediate step when cyclically permuting its digits will be another prime. Of course, this is to the base 10. For example, 1193 is a circular prime since 1931, 9311 and 3119 are also prime numbers. Other examples are 13, 17,
37, 79, 113, 197, 199, etc. These are all circular primes.
60 is another important integer. It forms the basis for measurement of time as well as angles in minutes and seconds. It can be written as the sum of two adjacent primes, 29 and 31, the so-called twin primes.
Now, there is an important function in the case of primes, the prime counting function, which is represented by the symbol pi of x. So, this is the number of prime numbers less than or equal to some real number, say x. It is denoted by pi of x. Pi of x is in fact a discontinuous function, as one can see from the plot given here. This is pi of x as a function of x. So there is a general increasing trend, but in between you can see that there are constant regions. So there is a discontinuity whenever we reach a prime. So therefore this function increases by 1 each time x crosses a prime number, and remains constant until the next prime number is reached, and so on. So these flat portions indicate the emergence of one particular number, and this continues until the next prime number is reached, when there is a step increase by 1. So the number increases by 1. There is an important theorem in prime number theory called the prime number theorem. This states that for large values of x, pi x can be approximated by x by log x. That means limit x tending to infinity of pi x by log x is equal to 1. Now let us look at some of the applications of prime numbers in various fields. First, we take up cryptography. In the field of information theory and communication, prime numbers play a decisive role in ensuring the integrity and security of transmitted data. Security, in fact, needs encryption of the data at the sender's end and then decryption at the receiver end. So that some eavesdropper somewhere on the line, although he may be able to grasp the data, but he may not be able to decrypt it, so that the information will be intact. So the principle of cryptography is illustrated here. We have some information, let's say the hello, it is first encrypted. So the first process is encryption. There is a particular key according to which this encryption process is carried out. Then this is what is called cybertext. That is the encrypted text which is sent over the internet. So at the receiver end, the pattern is received and then it is decrypted. So there will be decryption key at the receiver's end, and he will decrypt the message according to this particular key, and he will get back the text which was originally sent by the sender. So this is the principle of cryptography. Now, how does the prime numbers come into the picture here? See, it is in the process of prime factorization. So encryption and decryption depend on finding the only one pair of prime factors of a very large number, which are called semi-prime numbers. Of course, the large number itself is not a prime, but it can be written as the product of two prime factors in a unique way. So when the number gets very large, this is not an easy task. There are many crypto systems. For example, what is known as the reversed Shamir-Edelman (RSA). So this particular one uses large primes to construct public or private key pairs. The security of the RSA scheme relies on the fact that in general it is computationally expensive and difficult to identify the prime factors of a very large composite number, which are called semi-primes. The security of countless online transactions and their sensitive communications hinges on the inherent complexity of prime factorization. This demonstrates the practical application of prime numbers in safeguarding information. Quantum mechanics also has influenced the study of prime numbers through the development of quantum algorithms for factoring large numbers, such as the Shor's algorithm. Again, prime numbers and quantum mechanics are connected through various mathematical and theoretical concepts. That is, in fact, prime numbers go quantum. For example, consider a quantum system like a quantum billiard. The distribution of energy levels in such a system may exhibit patterns which are related to the prime numbers, thereby affecting the behavior of the particles within it. Again, the frequency of the non-trivial zeros of the Riemann zeta function, this is a very important mathematical function. So, the frequency of the non-trivial zeros of this particular function appears to have a profound relation to the discrete energy levels of large quantum systems. For example, energy levels in a nucleus of a very heavy atom has been revealed in reactions involving low energy neutron. So, this has particular relevance to the non-trivial zeros of this zeta function. Now, what is the Riemann zeta function? It is given by this particular summation, sum over n of n raised to minus s, n ranging from 1, 2, 3, etc. up to infinity. Now, one way in which the zeta function can be expressed is known as the Euler product formula. That is 1 by 1 minus 2 raised to minus s, 1 by 1 minus 3 raised to minus s, 1 by 1 minus 5 raised to minus s, etc. That is product over the primes of 1 by 1 minus p raised to minus s. This particular function is asymptotic to and is particularly good estimate of the distribution of primes. Another example is an electron constrained to move in 2 dimensions and subjected to suitable electric and magnetic fields have energy levels that match the zeros of the zeta function. So, thus indirectly these are related to the prime numbers. Now, prime numbers have important relevance in music and acoustics. In music theory and acoustics, prime numbers relate to what are called the harmonics. That means the waves which have frequencies which are integral multiples of the fundamental tone. For example, when you play a note on a musical instrument, the overtones or harmonics produced are related to the prime numbers. The first overtone corresponds to doubling the frequency, the second overtone corresponding to tripling the frequency, and so on. Remember, these 2 and 3 are the first 2 prime numbers. In the usual 12-tone scale in music, an octave is divided into 12 tones. The frequency of each tone is 2 raised to 1 by 12 times the fundamental frequency. So, in the familiar Carnatic music, we have the Saptaswaras Sa, Re, Ga, Ma, Pa, Dha, Ni, etc. So, if we take the frequency of Za to be 240, then
Re has 2 frequencies, 256 and 270. Ga has again 2 frequencies, 288 and 300. Ma also has 2 frequencies, namely 320 and 337. Has only 1 frequency, 360. Again, Dha has 2 variations, 384 and 400. And finally, N has again 2 variations, 432 and 450.
And the Sa in the next octave will be simply 480, which is double this particular frequency of the Sa in the previous octave, and so on. It is seen that the presence of overtones with frequencies in the ratio of prime numbers eventually enhances the melody of the music rendered.
I will end this video at this point.
If you like this video, kindly click on the like button and share with your friends and relatives, and also with your different groups. If you have not already subscribed to my channel, Murali's World of Physics, kindly do it now. And please don't forget to click on the bell icon so that you will receive notifications in future about my upcoming videos.
I'll be back soon with another video continuing our discussion on unique numbers in mathematics and physics. Till then, goodbye.